Well folks, Sean here from SMD Methods. You're all very welcome into this video. This video will be the first in a series of videos that's going to look at the design of a front wing for a Formula student car application. Now, it is similar enough in a lot of the procedures to what was undertaken in the other playlist on this channel, which looked at design considerations for the front wing of a STEM racing car application. Now, there's going to be obviously notable differences. The primary difference is that we actually want to generate downforce in Formula Student, where in STEM Racing we didn't. And for that matter, we're going to be looking at completely different aspects of the wing, but the workflow is going to be more or less the same. We're going to look at a 2D version of the wing. I'm going to include a wheel tire assembly in behind it as well. But what I'm going to do is look at configurations of main elements and flaps, with respect to both chord lengths for each of the elements and as well as at angles of attack of each of the elements on an individual basis instead of one big global basis. So the wing will be designed in within the regulations of Formula Student, which all can be found, by the way, on the Formula Student webpage, which is on the IMechE, which is the Institute of Mechanical Engineers website. The competition, as you can maybe get a hint from it if you haven't heard from it or you're new to it, the objective is to build a single-seater open-wheeled race car to a certain set of regulations, with the view to racing the car on a circuit near you, on an annual basis and going through. So the competition is opened up to undergraduate students, I believe maybe master students as well, but also students that are studying foundation degrees and apprentices in the likes of technical or community colleges, once the course, I do believe, is accredited by a university. So teams, I don't think, are limited in how many numbers you can have in it. But yeah, there's certain aspects of the car that you want to make sure that you have done. Aerodynamics is not really one of them. Obviously, there's more points and all for aero considerations, but the main name of the game is to get a car on track so that you can race it. You need a chassis, you need suspension, you need tires, you need a steering system, you need a powertrain, an engine, or else an EV, a gearbox, a seat, steering wheel, and so on. Then you can race a car. That's the main objective. Adding on aero and all that is just to make you do that or make the car perform a little bit better in them dynamic tests. So yeah, keep the aero in mind, but if you're new to it here, make sure you concentrate and get the car movable on track within regulation so that it is safe and it's both and functional with respect to each of its systems as well. So if you haven't seen the playlist on the design considerations for the front wing of a STEM racing car application, which is it's a playlist on this channel, I suggest you go and have a look at that before going into this one as well, because there are certain procedures and there's certain things that I've done in that video that I don't intend on showing again in this video, just because I'd like to keep this moving ahead. There will be a brave few videos in this series because there's an awful lot to cover. For that reason, it'll be worthwhile at least looking at videos 1 through 4 maybe in that playlist, and there'll be areas such as how to get the coordinates for points on an airfoil profile and all, which I won't be doing here, but has been covered there. So yeah, have a look at it anyway. I will put a link into the description, by the way. Yeah, you have no excuse. Right, so I'm going to jump on straight ahead here. I'm sure we'll do an awful lot of talking as we go through this. I'll explain why I'm doing certain things as I go. Yeah, hopefully you get a little bit out of this, and this will help you get a nice aero performance out of your vehicle, or at least out of your simulation. So opening up Ansys Workbench, first off I'm going to come into units as I always do, and I'm going to change this down to a more appropriate unit for our analysis, which is going to be in millimeters. And yeah, what I'm going to do is I'm going to pull in an analysis system. Now in the STEM Racing playlist, what I did was I brought in a component system. So I brought in a meshing component system, which dealt with the geometry and the meshing, and then I brought in the fluent flow, which dealt with the solver and dealt with the results. I still prefer that setup, the one there that I've always used. But for the workflow that I'm following this, where I'm using parameters really to drive the geometry, the analysis system seems to lend itself somewhat better. So with that said, I'm going to bring in an analysis system for Fluent, Fluent being my chosen solver in this. Now, the name of this system I'm going to call an E423. So I'm going to use an Eppler 423-ME for a main element. So my idea here is that I'm going to do a CFD on a single element wing first, a main element, made up of an Eppler 423 airfoil. And then what I'll do, once we get an idea of the performance of that, what we'll do is we'll shorten that main element slightly with respect to chord length, and we'll add on a flap. We'll check that. And then what we'll do is we'll shorten two of them and add on a second flap and check that. Our objective here is to get an appropriate amount of downforce onto the front wing. Now, here it's only a 2D analysis on this. We're never going to be able to fully appreciate the lift or the negative lift or the downforce, whatever you want to call it, off the front wing using a 2D analysis. And we're certainly not going to be able to accurately predict the drag, because 2D analysis, especially if we do it with a steady state solver, isn't going to take on sources of drag and sources of energy, whether we're energizing or losing energy from the likes of vortices and that. So yeah, it's going to be very preliminary at the start, but what it's going to allow us to do is get some sort of a grip on maybe angles of attack, slat spaces, between the different flaps, the type of airfoil that might help us, the effect on how the airfoil air interfaces with the wheel tire behind it, certain things like that. It would definitely worthwhile, give us a little bit of insight. So we are going to use it. Now, if you are doing a parametric study and you are changing the physics of the flow for the most part, so you might be, say for argument's sake, or the physics of the discretized space independent of geometry. So if you're changing the amount of elements, if you are in from a solver point of view, if you are maybe changing what can you say, velocities, inlet velocities, if you are changing maybe temperatures at boundaries and so on, yeah, absolutely go with the best CADing package that Ansys gives you here, right? If you or outside, you can use the way it's SolidWorks or Fusion or Inventor, whatever you like. Import the step file, and then you could fix the step file up. Typically would be Space Claim or Discovery. Now, in the last series that I did on the stem racing, I says, right, I'm going to try to do everything in Discovery. I said that. Why? Because Ansys is getting rid of Space Claim in 2027. It's removing support for it, and it's moving all its eggs into the basket of Discovery. For the better or worse, I don't know. However, Space Claim itself it seemed to be a wee bit handier to use in Discovery, but it was absolutely atrocious for getting parameters established. It wasn't just a straightforward get a parameter. You had to use a ruler tool and click a wee box, or go into your groups tab or this or that. And a Space Claim was bad at that, and Discovery was absolute poo. Discovery, you cannot get a parameter out of Discovery. I've been using Ansys for an awful long time, and I'm just not feeling Discovery here at all. A Space Claim. Now, if you're doing a parametric study that the parameters are principally solver parameters or variables, use away at them. CAD packages at Space Claim and Discovery. However, if the parameters that you are using are to drive geometry, to change the likes of chord lengths and maybe angles of attack, if you don't want to change the angle of the air coming in, if it's the actual geometry you want to change, you cannot use Discovery or Space Claim. You have to go to Design Modeler. Design Modeler might be a wee bit clunky. It might not be the most smoothest of workflows with respect to developing a CAD model. But it is absolutely phenomenal for creating parameters, and it's absolutely phenomenal to allow parameters to morph and change the CAD, which is what we want to do in this application. And you'll see why as we get through it. So I am going to use Design Modeler here. Okay, definitely going to use Design Modeler. So we're going for a 2D analysis, and let's open up a Design Modeler geometry. So what I want to do in this first is I'm going to bring in the profile, a 3D curve, and I'm going to bring in the profile of this airfoil. So I'm going to go onto the XY plane. I'm going to create a new sketch, sketch 1. I'm going to F2 that, and I'm going to call this one here airfoil profiles. So airfoil underscore profiles. Why profiles? Because when I copy and paste this analysis system and I put in a flap, right, I'm going to have a second profile, even though at the minute I'm only having one. So I'm going to look straight on this here, make it a wee bit handier. Airfoil profiles is lovely and live. I'm going to come on into concept, 3D curve, which is not a sketching tool. This is part of the modeling package, so it doesn't really matter that we're in this work plane. Point selection, no, I have no points. I'm going to go to coordinate file. My coordinate unit is going to be millimeter, and the coordinate file I'm going to browse myself to lives and my OneDrive, training, CFD, airfoil data, Eppler 423, 2D, and I'm going to go for this one here, this text file. E43 coordinates DM for Design Modeler 2D text. You see I have a separate one here, DSCO is Discovery and Space Claim. They both have the exact same coordinates in it, but the format is slightly different because Design Modeler takes the coordinates and it'll only read this file if it's in a very specific format, as is the same with the Discovery. Now, what they look like is in here. So again, as I said, I'm not going to go over everything that's in this. If it looks completely alien to you, it's probably because you haven't looked at the other videos. Have a look at them. But basically what it is Design Modeler here needs 5 columns, including the Z coordinate, groups, and a count of points, whereas Discovery Space Claim need only the 2 columns, if it's 2D, X and Y, the group column, and then I also need to include the polyline being true or false. I usually go for false on that to use a spline. This incidentally is the format that we need if you want to import the coordinates, these points onto the coordinates in AutoCAD. If you want to develop, say, a DXF or DWG in AutoCAD, you'd use that format, which incidentally itself is not a text file, it's a script file and a CR file, which we could see there. There's the script file for it. So anyway, I'm going to bring in the Design Modeler. Open. Now there's no errors in that. Now here's something for you as well. I'm going to go as far as to say, if you haven't done this before, 7 out of 10 of you are going to get an error here when you try to bring this in. If you don't know how to bring it in, right? And again, I'm digressing slightly, so please bear with me on this because it is worth knowing. It might just save you half an hour of that figuring out what's gone wrong. Whenever you bring in the coordinates here from airfoil tools, that's them there, right? If you have selected that you want to close your trailing edge, what you're effectively going to have is this point at the trailing edge, 100, 0, if it's 100 millimeter chord length, and then we have 100, 0 at the end. That's the close. So we have 2 points, 2 geometric points there on one coordinate. That's 100%. In Discovery and a Space Claim. It does not mind having 2 points on the one coordinate. So these are the coordinates. So why is this 100? Why is this 99.98? Go back and look at the other videos and I'll explain why. Right? But what we'll have is the same point here at the start and the same point at the end. That's fine. We can import a closed airfoil into Discovery and in Space Claim. We cannot do that in Design Modeler. So what you'll note here in Design Modeler, I have my first point, 98 or 99.998 and 0.088 here, right, which is these two. However, my last point here is 99.627 and minus 0.018. It's not the same as the first point because Design Modeler will not allow you to have 2 points onto the same coordinate. So that's why I've just put this in here as a reminder for myself. Of course, at one stage I had this dimension in here as well. So I have to take that out. Don't bring that in. My text file goes from here all the way, of course, up to there. That's it. Control C, open up Notepad, Control V, save, and Bob's your uncle, save as text file. That's why I have no error in that. Millimeters, XY plane, add material. Yes, I'll add material, and let's go for a generation. Right. I'm going to zoom extent. There it is, and we can just about see the airfoil here. Go into the darker region. It's a wee bit handier to see. I'm going to scoot it round, rotate it round here, so we get this big old vector out of the road. And we could see here now that we have trailing edge that is not closed, right? I cannot create a surface from this. I want to create a surface onto this, but I cannot create a surface on this just now. Can't create a surface on this until I close this edge. So what I'm going to do is come back into concept, I'll go to lines for points, and I hover over the end of this point, and I see a wee black box. Click that, hold Control, go over to the end of this line here, see a wee black box. When I hover over it, click, that's with the Control, and there is our green line. When that's in there, let's hit Generate. And there it is, add material. And now we have an absolutely lovely closed curve. And so appreciate it's hard to see there. Bring it up in the darker region, you can see it a wee bit better on the screen. Okay, stop right at that. Bring it on up. There it is. So what I'm going to do now is I'm going to create a surface from that. Okay, so we'll go into concept and we'll go surfaces from edges. I'm going to click that edge, and remarkably, I scrolled all the way out just so I could scroll all the way back in again. Right? I'm going to hold Control, and I'm just going to pick up that wee point there, right? Coming closer so you could see it. Hit there, that wee point. Click that wee point as well. There's my closed airfoil. When I have them all clicked, I can hit Generate, and let's just zoom extent. And there is my airfoil profile. Now this airfoil is a 100mm chord length airfoil. I want to make this bigger. How much of a chord length do I want in this? Well, Formula Student regulations state that the foremost point, the leading edge of my front aero element cannot be more than 700mm in front of my front tire. So I'm assuming there that the front, what they mean is the front tire is going to be a line that is tangent to the tire and normal to the track at the front side. So if I drop a line there and then I move out 700mm, right, that is as far out as my wing can go. I can't bring it out any further. Why? Bring it out any further, the competition organisers and scrutineers rightfully would be concerned about driver visibility, the driver's ability to see the track in front of them. If there's a big massive wing in the front, it doesn't really help to see cones that you need to drive around. So yeah, 700mm is as big as I can make this airfoil. Now if I make it 700mm, that means that the trailing edge is going to be rubbing, well, it shouldn't be rubbing the tire, but it'll just be coinciding with the tire. Okay, which I don't want, right? Do I want to make it 600mm? Well, if I make it 600mm, I could leave a 100mm gap, 4-inch gap there. That's not bad. Now, the other regulation would state that the trailing edge of the wing cannot be more than 250mm, or well, any part of the wing cannot be more than 250mm above the track as well. Which means that if I am putting an angle of attack in that, that'll more than likely be the trailing edge that'll be up high, which is the edge that's closest to the tire. If we use a Hoosier tire, depending if we're going for a 10-inch or we're going for a 13-inch wheel, it will make a difference. But if you're going for a 10-inch, say, just taking the first one that shows up on the website, the trailing edge is just a wee bit above the hub of the wheel, which means there is an awful lot of tire still above the airfoil. At the rear of my airfoil is very close to the tire, 4 inches say, and I have maybe up to 10 inches of wheel still above it. You know, I have this overpowering wheel, you know, just right at the back of the airfoil, not far off the back. I don't know. It could work fine, but I'd prefer to give myself a wee bit more space on that, because I might be able to do something with that air, before it comes onto the tire, or maybe direct it off somewhere, have a little bit more interaction with the end plates, or put strakes on in some case. But nevertheless, I want to leave a little bit of space for the conditioned air that's coming off of the airfoil to do its thing before hitting the wheel and the tire. So what I'm going to do is I'm going to leave 6 inches, 150 mil, which would mean that this airfoil will be a maximum for me of 550. Now I can make it 400 if I want. I can make it 300 mil, but I want to be able to generate a certain amount of downforce on this, right? So I want to be able to show the judges and the scrutineers that this is the sort of downforce that this wing can, by simulation study, achieve. That is important because if you enter the competition in around end of December, January, you need to send in a design concept specification, and on that, you may be asked, or you may have put in, what your target downforce is going to be. What sort of negative lift are you aiming to achieve with aero elements, maybe to the front and the rear? You have to, if you talk about it, you don't want to pull a number out of the sky. You want to have a number that makes sense, a number there that you are designing to. And then later on in the competition, April, May time, start of May of that, you have to submit your design specification. And also you have to submit a spreadsheet full of fun facts and figures about what you've found with respect to different systems on your car, including your aerodynamics. Is what sort of downforce are you looking to achieve? So if my wing is too small, I'm not going to generate the levels of downforce that I want. And the other thing is I want to generate these levels of downforce at a relatively low velocity. And I'm not a 747 here, number one. In fact, I'm not even a Formula One car here. In fact, I'm not even a STEM racing car here, where I'm looking to generate this downforce. Yes, this car will move fast, but it's not when the car is moving fast that I want downforce. It's when the car is moving at a relatively low speed, low to medium speeds, because it's on them low to medium speeds corners that I want to keep the car pinned onto the road. So any downforce I am looking to achieve, I am designing for these corners, not for the straights. I have big downforce on the low to medium speed. It means I have an absolutely phenomenally large, massive downforce on the straights, which isn't good, but that's have to be dealt with in another way. I mean, bring in some active air or DRS if you want. But the thing about it is I am going to be looking to achieve a certain amount of negative lift at a low speed. So I want to have I'll need a fairly substantial airfoil to do that in principle. Okay, so that's where we're going to start with. That's the starting point anyway. Well, we can optimize that and we can bring it down as we learn new things, as we bring in angles of attack and different flaps and different profiles and so on. So we'll keep that one in the back pocket. So what I want to do now is I want to give myself some provisions here that will allow me to scale this airfoil up and down, and also to change the angles of attack. Now, whenever we're changing the geometry in this, you have to be very careful, because after it's meshed, the meshing elements are going to have themselves arranged in a very particular manner in around the airfoil. So it's not just a matter of mesh size, and it's also a matter of mesh fitting, which is a function there of the orthogonality and the skewness and all of these. Whenever that's resolved and we'll have a nice mesh made, all it takes is a small little jink in the geometry, and what that'll do is it'll throw the mesh completely off. Now the mesh will kind of resettle itself on every iteration on a design point with changes to the geometry, but if the changes are very small, what tends to happen is that we'll see some, we could be moving into singularities within the flow domain, within our discretized space, where we're getting artificial numerical inflation, especially in areas in there around the trailing edge and that. So what I want to be able to do is I want to be able to modify this airfoil without affecting the meshing around it. Right? I want to protect the meshing in around this airfoil. So this is how I'm going to do it. Now, I haven't done this before, so please bear with me. It's just an idea I had because I was footering around with changing angles of attack on geometry through parametric studies. And what I was finding was that if I was at 8 degrees, everything looked good. 10 degrees, everything looked good. 12, everything looked good. But the angles of attack in between that, say going from 8 to 8.5, 8.5 was desperate. The drag was going up by 10 orders of magnitude. You know, it was completely wrong. And what I have that put down to is them singularities that were created through the very small increments on the angles of attack, and the resultant skewing of the meshed elements. So what I want to do is I want to alter this now, but I want to alter so that when I change the geometry of the airfoil, I change the mesh with it, the mesh locally to the airfoil, that is. So this is what I'm going to do. I'm going to go ahead in and I'm going to draw I'm going to go for an ellipse. I maybe thought about going with an oval, but I'm going to go with an ellipse because I kind of want to stay as best as I can with this curvature. I'm going to try to keep the ellipse as tight as I can around this, because if I draw on other elements and I draw on other bits, I don't want the ellipse impacting with other pieces of geometry. So I'm going to try to get the center. I'm going to see what we go for if we want, say, from here. I brought it this way, so I'm too far already, I think, to the left. But we'll see. Cover off I can move this, of course, but I'm going to keep it big first, because when I bring it in this way, it is very big. If I was to move that back, I probably can. I'm going to try it there, and then I'm going to click that. I'm going to go to modify, move, click on it again, and see what I'm like. I want to keep this section here tight because I'm going to draw on a track, and I want to keep this section here at the trailing edge tight because I'm going to put in a flapped element here later on, and I don't want it to impact this. If I rotate that around, so I'm still in there, but I also want to make sure that I don't interfere with my boundary layer, so I might just need to give that a wee bit more. I'm going to go again to move. Just a wee bit more, just so I can get the boundary layer in there. Don't want the boundary layer to go outside of that mesh. Probably can go maybe just a slight wee bit more here on the trailing edge. Maybe bring it down a wee bit. Move. I'm gonna try it there. The boundary layer should be well within it there. Well within it there. Well within it there. All right. I think I'm gonna try this one. All right. Let's look directly on at this. Sorry, there we go. Now I'm going to create a surface. I'm going to make this into a surface. So let's go on into concept, surface from sketches. Let's create that, and let's apply that. I'm going to add frozen here because I added material for this airfoil profile. So I'm going to add frozen and generate, and there it is. All right. So now that we have our airfoil enclosed in the ellipse, in this kind of bubble wrap, if you like, what I want to do is I want to scale. I'm going to apply the scale now. So as I said, we have 700 millimeters effectively between the leading edge here up to the front tire, and I'm going to make this 550. So this is what I said a wee bit earlier on. So to do that, what we're going to do is go into create. I'm going to go to body operations, and I'm going to go to scale. Scale is going to be ME. Scale ME. Just call it the scale so I can know what it is here. Preserve the bodies, no scale and origin, world origin. So I'm going to scale this from this point here, right, from the leading edge at 0, 0. So again, the leading edge is at 0, 0. Bodies, apologies, bodies are going to be these three bodies. So this wee line body that I had, this surface body, which was the main element, and also my bubble wrap, if you don't want to call it that. Bodies apply. There's three of them to be scaled, uniform scaling. Right? I'm going to make this 5.5 and generate. Now, what I'll do is I'm going to switch off. Sketch is fine. I can turn off that airfoil profile sketch. I'll just leave it there for now because I'm going to do a rotate as well, and I'll keep that. Now, what I'm going to do is I'm going to click that on as a parameter, right? So this is going to be scale dot me, main element scaling. Okay, so this is the beauty of Design Modeler. So easy to create a parameter on it, and this parameter here is driving geometry. The parameter is going to show up here on the design table. There it is there, scale.me at 5.5. It's a 100 millimeter based airfoil, so when I scale up by 5.5, it's going to go to 550 millimeters. And that's what we're looking at here. All right. Again, I could, in my design table, I could change that to 4 here, and that would scale that back to 4. I could change it to 2, change it back to 2, okay, to 200. So I can scale it up and down. Design Modeler facilitates parameter-driven sketching, parameter-driven geometry transformations, which is so handy for these sort of parametric studies in which the geometry changes, or we're looking at different geometries for the same physics, as opposed to what a lot of times we're looking at different physics on the same geometry. Okay, so there is the first transformation of this. Now, the next thing I want to do is I want to be able to rotate this. I want to put in an angle of attack. So I'm going to go to Create, Body Transform, go to Rotate again. Rotate, this is going to be Rotate, what did I call it? I call it other thing, Scale 3, Rotate ME. Scale 3. I need to generate this before I change the name on that. Rotate ME, preserve bodies, know what bodies I want. I want all three of these bodies again. I want to rotate all of them. Apply. Axis definition is going to be by selection. The axis selection is the XY plane, which is going to be my Z vector here. So interestingly enough, in this application, the Z vector is going into the screen, not out of the screen. So normally you would associate the Z vector coming out of the screen, but for this rotation, right, we're going into the screen. So I can flip that over to put it out of the screen. That's very important, okay, because if you, as you do know, you know your right hand rule, all right? So if we're coming out of the screen here, right, our thumb is coming out and we're rolling our fingers around on the positive angles. If it's going into the screen, our positive angle will be coming round on the clockwise side, our negative angle in the counterclockwise side, negative angle, yeah, which would be counterintuitive to how we would normally associate our angles. Our positive angle definition would normally be in the counterclockwise direction. So if I look directly on that, I've changed my arrow. If I go for axis selection, apply, right, we can see here that a negative 15 degrees, right, has scooted my trailing edge up. So the negative angle here is still going up with the in the counterclockwise direction. It's giving me a negative angle. But there you have it. If I go with 15 degrees, it drops me down. Right? 0 degrees puts me back at my neutral angle of attack. But if I go for, I'm going to try minus 15 degrees on this one. I'm going to go to there and generate. Now I have my whole entire flow domain scaled to 550 millimeter and now at a angle of attack, and that includes my cushion. So every time, and when I say my cushion, I mean my box going around this here, my ellipse. So every time I scale my airfoil up or down, anytime I rotate my airfoil, I'm not only going to rotate the airfoil, but I'm going to rotate this area along with it. All right, so that's hugely important, because that means all the meshing elements here that are local and pushed up against the airfoil wall will not change. There will be areas out along here that'll change, but that's fine. I'm not, the physics there is just not as intense. I'll specify this boundary as an interface layer, an internal layer, and an unmapped mesh. We should be able to go into this and out fairly handy, but we'll see how it goes. Let's see what happens. So what I want to do now, the last kind of bit on this, is I want to draw in the flow domain. So to do the flow domain, what we'll do is we'll stay on the XY plane. I think is there any worth going into a new plane? I'm going to go onto a new plane. Right, I'll call this plane here the flow domain plane. Why not? Generate. So I'm in the flow domain plane. I'm going to do a sketch in here. Right, F2. I'm going to call this one the far field, maybe. So this is going to be my overall, my huge domain. Now I'm going to do a C-type domain on this. However, the C-type domain, I'm going to also put in a track, so it's going to be kind of half a C-type domain. So have a look and see what you think. So I'm going to go into sketching. I'm going to take a line. Now what I'm going to do is I'm going to drop a line from the origin P down some arbitrary distance. Don't really care what it is just now, because I'll dimension it up and I'll fix it up later on. I'm going to take a line from P and I'm going to come out here again, a distance. Now this distance is, however, important. All right. So the distance that I want to come out here, go into dimension, just take a general. Let's script that and bring that down, H1. Right, this is in meters. Let's go into units, millimeters. H1. This is going to be the inlet. This is going to be my upstream section of my flow domain, or of my flow field, upstream of the airfoil. So we're not going at massive velocities here. As I said, it's not a 747, so I don't think that there's any need in going out, 10, 15, 20 chord lengths out in front of the airfoil. I'm going to go out five chord lengths. Right? We'll be much more interested in what's happening at the back at 15, 18 meters per second. We're not getting massive compressibility effects. Anything at the front, disturbance in the air, no, not so much. So let's keep it relatively modest at 5 chord lengths. So with a chord length of 550 millimeters by 5, 2750. Well, 2750 is my chord length there. Right, when I have that, I'm going to now come in and I'm going to go to an arc by center. I'm going to click this wee point down here, so you get a C and a P. Right? I always like the P's. Right? And I come out to this P, and then I'm going to drag this here, control, and drag that down to hit a C up here. Okay. Now what I'm going to do is I'm going to take out that little line that I had in for a bit of construction. Zoom this on out. I'm going to take another line, take it from that P, come out some arbitrary length, go on into dimension. Let's dimension that one. This is coming not all downstream of the airfoil, because there's a wee bit of the airfoil in it. But what I'm going to do, I'm going to come down, I'm going to go more than 10 lengths. 10 lengths would be 5,500. I'll go 15, which would be another 2750 on top of that, which would be 8250. 550, 8250. Let me just double check that one. I'm not as confident with that. It is very late. 8250 was right. Yep. Right, and now what I'm going to do is I'm going to take another line, draw line from P, get a V, hit a C, and what we'll do is we'll bring that, oh, actually I hope it just, I'm going to take that one away because I don't want it to snap onto that point in case. I'm just going to get a P and just drop some V, and then what we'll do is modify, let's go for a corner, let's take that one, tell that one, and there's a nice flow domain in there. All right, now I can generate a surface on that if I wanted to just now, but I don't want it just now. What I want to do is I want to put in the wheel and the tire into this as well. Okay, so what are we going to do? Well, let's go on into draw. Let's take a circle, and we don't know where the wheel and the tire center point is going to be just yet, or what size it's going to be. Let's just stick a wheel in here. Right, so we're going to have to dimension this wheel. So wear and tire, where am I going to go for that? Now, what I'm going to do is I'm going to scoot myself on into here. They're the racing tires. So the racing tires I can see come in 10 inches and 13 inches. Right? That's because there's OZ wheels, provide wheels for Form Student. I'm sure there's others as well that do it, but OZ wheels have it. I can see 10-inch wheels here at the top and 13-inch wheels. Seem to be 1, 2, 3, 4 13-inch wheels and 2 10-inch wheels. However, in Formula Student, most of the tires are 10-inch. So we'll go for a 10-inch. That's what most of them are. So a 10-inch tire, outside diameter, and this one here is for 18. It's slightly bigger. It must have a larger sidewall on it. That's a bigger radius. Just take the top one here. Let's go for 16.3 inches. So let's go for 16.3 inches multiplied by 25.4 millimeters per inch. Means 16.3 inches is 414.02 millimeters. 414.02. That will be the diameter of my tire here. D3, let's make 414.02, and what I'm going to do is I'm going to make that into, I'm going to put that in 414.02 millimeters. It's very small, isn't it? Maybe that's all it is. I'm going to make that into a parameter anyway, and let's call that keep that in small, tire. I'll keep it in large. Tire dot diameter. Tell you what, I'm not going to put that in just yet because I'll tell you why. I should have made my angle of attack here. Where's my rotate here? Rotate ME is -15. I had fully intended of making that a parameter. So I want to do this one because I want it to appear first in the parameter table, design point table. So instead of calling this rotate ME, I'm going to call this AOA, small o, AOA.ME, angle of attack ME. Now let's get back to where was I here. This diameter here, D3, let's call that wheel diameter now. Wheel dia 414. Right? So we'll make that. It's getting late. Wheel diameter. Okay, there we are. Hopefully that did it. There's the wheel diameter. So if I want to, our tire diameter, parameters, tire diameter, thank you, generate, it's better, take that away. Right, the center point, let's move on, horizontal from the leading edge of the airfoil to the hub of the tire and wheel. We're into H4. So what distance should that be? Well, as I said, I know from regulation that the maximum distance between the front of the airfoil and this leading edge of the tire is 700 millimeters. So that's 700, and then the radius of that tire would be 207.01, would take me into the middle. So that leaves us 700 plus 207.01 gives me 907.01. That's going to pull my wheel and tire up to there. Now what I'm going to do is I'm going to parameterize that as well. Right, so I'm going to say I'll call it wheel, and we'll keep this wheel dot to LE, leading edge underscore airfoil, leading edge underscore ME, main element. How's that? Okay. So just in case there that I want to bring my wheel a wee bit closer. Gives me a wee bit of flexibility that way. Now what I also want to do is I want to set my height. Right? So I'm going to set from here down to this one here, which is going to be my track height, V5. So you would naturally think here, surely that should just be the radius, right? Which it should surely be 207.01, but let's have a look. When I do that, I'm going to say that this vehicle traveling at whatever, 15 meters a second, 18 meters a second, the speed that I want to generate a downforce at, that's all the size of the contact patch it has. That's completely unrealistic. All right. Now I know this is CFD, unrealistic in a lot of cases is the name of the game, but we could probably do a wee bit better here. We should have a larger contact patch there, so we should have some squish in that tire. So instead of going for 207, I'm just going to go for 205. I'm going to bring it down closer. And what I can do then, right, is I can come on into modify, right, and I can trim, right, and trim out a piece of the track there, and trim out a piece of the tire there. Right, and now I have a flat patch here. Right, so a larger contact patch, still not huge, but at least it's somewhat more indicative of what we might find. Now the next thing is the height off of the surface of the track of the airfoil. Right, so it's really this lowest surface that I need to find the distance from. So I'd like to go from there to here, but I can't pick anything up here. Best I can do, what did I do there? Let me just undo that because I trimmed out that. I hit trim. I meant to click on dimension, general, go from, not that to really there. I can't pick up that anything there, but I can pick up, and take that off, go vertical from here. There's nothing that I can pick up here on this bottom edge, but I can pick up indeed the origin though. So what good is that to me? How do I know what the distance is for that? So say for instance I set a ride height here. How do I know how much more I need to go to come up to this this origin point? Well, I've carried out that exercise here. All right. So this is an Eppler E423, an Eppler 423. And this is showing me the distance between the lowest point in the airfoil and the world coordinate origin for different angles of attack on a 100 millimeter airfoil. On a 100 millimeter airfoil, right? So 11.06 at 8 degrees angle of attack up till 7.87 at 15 degrees angle of attack. So obviously there, the more I tip the airfoil up, the trailing edge of the airfoil up, the closer and closer the nearer this lowest edge gets to the pivot point, which is round here. So at 15 degrees, that's the distance. Right? Now that there is for a 100 mil airfoil. So what I've done here on the spreadsheet that I keep all my airfoil data on, I've added in this table here. Right? So normalized to a 100 millimeter chord, because this is what all this data is given for. From -8 down to 15, I've just put in the values that are measured off AutoCAD. And then I have this LE to track, which is based on my target chord length and my target clearance. So for a 550 mil chord, right, cleared off the road by 42 mil, at 15 degrees angle of attack, that there is that height, that vertical height between the world coordinate origin and the track top, 85.29. Okay, if I wanted a 30 mil, 73.29. All right, I can change them, and indeed I can change my target chord, right? So if I wanted to make a 400, they'll all update there accordingly, right? So there you can see the formula for it, so you can take that formula down and use it yourselves if you like. That's how I've worked it out. Now, the next couple of videos will show how I can streamline entering in this data. So V7, this here is at a 15-degree angle of attack for a 550mm airfoil. So that distance, 550, and I'm going to go for 42mm clearance, 85.29 mil, 85.29. That comes up to there, 85.29. Now I have a 42mm angle of attack, or clearance here, for a 15 degrees angle of attack. Now, if I was to jump into Workbench and I change my angle of attack to 10 degrees, that would mean that I would have to go in here, check 10 degrees, 97.28, and then update this here to 97.28. That's something that I don't want to do, right? I'm going to parameterize it, but I don't want to have to change 20 different parameters every time I change an angle of attack. Literally, I just want to change an angle of attack and I want everything to update. So I can do that in the properties window in Workbench, and it makes it very slick, very streamlined, and we'll look at that in the next video when we get into it. So what I'm going to have here, I'm just going to call this LE dot to track, leading edge to track height. And remember that. In fact, what I'm going to do is I'm going to create a new parameter. I'm going to call it ride height. I'll put in, excuse me one second. I'm going to put in a number, 42, 50, 30 mil, whatever it might be, and I'm going to have that update everything from the design point table. So there we are. Now I want to again split this zone into a couple of new bits. All right, so the first bit, what I'm going to do is I'm going to add in not a far field, but a new sketch. So I'm going to come back on into modeling. In my flow domain, I'm going to add in a new sketch, and I'm going to call this midfield. F2 mid underscore field, like so. Midfield is live. I'll come back on into sketching. I'm going to take in arc by center. I'm going to run from here. Right. I'm going to come out some length, don't know what, and bring it on up into here. Let's give ourselves a radius on that one. Dimensions, radius, boom. Radius on this one is, I'm going to make that 1800 just to round it off. 1800 is fine. All right, I'm going to then take a line, draw a line from here, come down to there, some length down from there, and then drop it into here. I'm going to dimension that. Where are we going to here? Just take general. Right, H9. Let's go till far field. Probably take that in a wee bit. Let's try 60. Let's try 4200. A wee bit bigger than that. Let's go 5400. Let's try 54. Go a wee bit bigger. Let's go 6000. Grand, okay, and that there is going to be a midfield domain. All right. In fact, let me just go for something here. Let me create a sketch here first. Concept surface from sketches. I'm going to take this sketch here first. Let's just see what this does. Generate. All right, that's good. Added material to that one. It's okay. Lovely. I'm now going to Yeah, let me go for tools. I want to face split, target face. Is that apply tool geometry? Come on into this. I'm going to select that, that. Apply. That's it, and generate. So now I have a body there, a body there. Nice. I want to do one more. Okay, just another face split in here. So I'm going to go to my flow domain. I'm going to come up with a new sketch and I call this near field. F2, near field. Near field's live. Come on into sketching. Same idea. Let's go arc by center. Let's take it from that point, P. Take it out again, some arbitrary length. Come up to the top. Let's dimension that. General, let's go radius. Both. This one here, let's make that we go 600. Should be all right. I think 600 should be good. Yeah, should be all right. Draw line. Take from P. Let's take it out again, some length to here, and then down to here. Again, dimensions. Take a general for this one. And this one, let's make 3600. All right. Let's now go to tools. Let's split the face. What face do we want to split? It's that one. Apply tool geometry. Select your edge tool and go for this one, this one, this one. Apply, generate. Okay, let's check. I have 1, 2, 3 different faces. Now I need to deal with this in here. I'm going to do a Boolean subtract now for this. So I'm going to come on into concept, or create Boolean subtract. Target body is this whole thing here. Apply. Oh, excuse me. Target body here. Apply. Tool body is that there. Apply and generate. So that's that there. Oh, not so much. Not really what I wanted to do there. Sure, it wasn't. What I should have done, I don't want to Boolean subtract that out. I wanted to actually Boolean subtract that out, but I wanted to preserve that tool body there. So that's what I did there. Where is my Boolean? This last Boolean, let's get rid of that. Which is that. Let's try that again. So let's go create in Boolean. Right, we're doing a subtract, but we want to preserve the tool and bodies. Yes. Target body is this. Apply. Tool body is that. Apply and generate. Ground. So there, I still have that body and I have that body. Now we're going to do another one. Create Boolean. Preserve the two bodies. No. Target body is that. Apply. Tool body is the airfoil itself. Apply and generate, and it's gone. Now, so what I have here is a empty region where I have my solid airfoil, empty region where I have my solid wheel and tire. I have a region in here which is going to be kind of my protection zone, mesh protection zone for the airfoil to stop any skewing or orthogonal problems whenever I alter my angles of attack. Out here I have a near field meshing here, so I can put that down to a very tight mesh, not obviously as tight as what I'm going to put in there. A midfield out here, and then a far field out here. Okay, now next thing I just want to make sure of on my my whole body here, sketching, modeling, airfoil profiles, planes. Let's just go down onto my surfaces that I have this as a fluid. On the fluid, right? This surface body. This one here, I'm going to rename that. Let's call this my my flow field or fluid flow field. My flow field there, and this one here, is going to be my, say my close region, my protection region. Call this maybe a buffer region. That's it. Okay, that there is how I'm going to set up my geometry and work a parametric study from it. Okay, so this has been a massively long video. There's been an awful lot set up on it, but hopefully the concepts will become clearer as we advance through this series. We do need to carry out a grid convergence index study on this, and we have to carry it out on a number of angles of attack, not just one. And we'll maybe do that in a supplementary video just to keep time and keep this moving. I'll likely not do it in this series, but again, the GCI process is laid out in that STEM Racing playlist, so definitely go back and have a look at that. But after that, yeah, thanks very much for joining. I'll be back as soon as I can with the next video on the meshing. These things tend to happen very late at night by the time I get read up with work on that and get sitting down and thoughts organized and so on. So it could be a wee while, but if you do hit the subscribe on that and the notifications when it does come out, which I promise I'll try to get it done in the next week or that to keep moving on, you'll be notified straight away. So yeah, thanks very much for bearing with me on the video. Again, I hope you took a little bit away from it, and yeah, hope to see you in the next video. Thanks very much.